Alrighty, let's go ahead and get started on part 2 of our adventures into optimization problems. Let's go ahead, and we may run into a few as we move forward that could have been done Algebra 2 style. That was mainly my way of sort of drawing on previous knowledge and put this all in context of stuff that you already know. We will, of course, have quite a few as we move forward that cannot be done in that way, and we'll sort of deal with those, in a rigorous calculus fashion as we encounter them. Let's go ahead and look at number 5 right here. Engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 500 cubic feet of water. What dimension should they use to create an acceptable aquarium with the least amount of glass? And this, of course, is a very common issue in terms of manufacturing. Of course, oftentimes it's much more robust than this. But if you're making an aquarium and you want it to hold a certain amount of material, you don't want to spend any more on materials than you have to. The less materials you have to spend money on, the greater your profit margin, okay? And so we can at least see here sort of a hint at the real-world application of this kind of thinking and the robust way in which we can actually use mathematics of optimization in order to find the answer to those questions. Now, first, probably a good idea, as always, to draw it, okay? And, I guess I've never claimed to be an artist. Okay. And, yeah, ish, right? Ish. Now, what we know is that the bottom, okay, we know that it has an open top, and we know that the bottom is a square. Well, that's great, because then I can use x and x for the area of the bottom, and I just need y right here, okay? Now, I have two different relationships explained to me in this problem. One is a surface area issue, which is, of course, what we're going to look to minimize, because the surface area tells us the amount of glass, right? So the surface area is the bottom, x squared, and 4 sides, 4xy. Now, of course, it's not 2x squared because it said very specifically that it had an open top, okay? So we have glass on the bottom and glass on the 4 sides all the way around, so that's the bottom and the 4 sides. But we also have a volume relationship. I know that x squared y is equal to 500. Now that's pretty significant because that means that y is equal to 500 over x squared. And that, of course, can be substituted in such that I now have a function of surface area that's going to be that. Once 4x is multiplied by this, the 4 gets multiplied by the 500 becomes 2,000, and this x is going to cancel out with one of these x's, just leaving a single x in the denominator. Now, some of you might actually want to look at it like this for purposes of differentiation. And notice that this is not a quadratic now. I could not use completing the square in order to find this maximum or this minimum, okay? So that becomes 2x minus 2,000 x to the negative 2, okay? Now that is 2x minus 2,000 over x squared, or if you want, it becomes 2x cubed minus 2,000 over x squared. Now, that's pretty significant once I've gotten that, because I know, first of all, that when I'm looking for critical values from a first derivative, I need to look at those points at which the derivative is either 0 or undefined. Well, it's undefined when x is equal to 0, which is a nonsensical sort of thing when you look at the, because basically if you have a base with area 0, then basically you have a you have an aquarium with a base of 0 and sides of infinite height and no width. So it just doesn't even make sense. What we are going to do, however, is we're going to look at this right here, because this right here, when I set that equal to 0, is going to be x cubed minus 1,000 is equal to 0, or x is equal to 10. X is equal to 10 is going to minimize, okay? And therefore, I know that when x is equal to 10, y is equal to 5, because I just very quickly plugged 10 into here. So that's going to be 500 divided by 100, so y is equal to 5. And it asked me, if you go back and look at the problem, it said, what dimensions should they use to create an acceptable aquarium with the least amount of glass? And so you would just write out, the base must be 10 by 10, and the height must be 5, whatever the units are. I think it was feet, cubic feet, okay? And that scenario right there represents a volume of 500 cubic feet and a minimum amount of glass used. Okay? So that winds up being, kind of nice. So it's 10 by 10 by 5. Let's go ahead and see if we can find another that will be good for us in terms of moving forward. See if I can find another classic one. You always want to do the classic ones. Oh, okay. Yeah, this is a related one, but since it deals with circles, there's always a possibility that stuff like this will pop up on an exam or something like that. A large soup can is to be designed so that the can will hold 16 pi cubic inches of soup. Find the radius and height such that the amount of metal needed is as small as possible. And that's the same logic that's going on here, that's going on in the previous problem. It's just the fact that this is a cylinder, whereas the other one was a box. But we still are going to be interested in surface area and volume, okay? So if we have, this is R and this is H, I know that the volume of a cylinder is going to be R squared H, right? Because it's just a rectangular prism, so it's the area of the base times the height, okay? Now we know that the surface area of a cylinder is going to be R squared, which is the area of the bottom, plus R squared, which is the area of the top, okay? So the area of the top and the area of the bottom is 2R squared. Now, you have to remember that the outside of that cylinder right there is really just a rectangle. So if you were to like cut it open and unfold it, right, what you would get is you would get something that looked like this, okay? So if you were to cut the top, cut the bottom, and slice this thing down the side and sort of unfold it, it would look like this. Well, we've already talked about the fact that this is R squared and this is R squared. You know that this is H. This side right here, this matched up with the circumference of these circles. So this is actually a rectangle that has the sides H and 2 pi R. So 2 pi R H. There's your surface area. Now that is what we're trying to minimize, okay? So if I'm trying to minimize that, oh sorry, all of a sudden I'm forgetting all of my pi's. That's pi R squared, pi R squared, pi R squared H, and of course I need a pi in there as well. I feel like that's a kind of a rookie mistake. So what we need here is we need to know that the volume needs to be 16 pi, so pi R squared H, that's what that needs to be right there, okay? Obviously, the pi's can cancel out, and here I have everything in terms of R except for that lone H. So it's probably a good idea to go ahead and use this to solve for h. So h is equal to 16 over r squared. That transforms this as surface area as a function of r into 2 pi r squared plus 2 pi r 16 over r squared. I'm going to give you a second to look at that. Always, remember, it's a video. You can pause it if you want to look back. Okay. Now this, when I simplify, is 2 pi r squared plus 32 pi r to the negative 1. And when we differentiate this, we're going to get 4 pi r minus 32 pi r to the negative 2. And of course, just like the last problem, this one can be put in terms of a common denominator. This is obviously 4 pi r minus 32 pi over r squared, which makes this 4 pi r cubed minus 32 pi over r squared. And of course, if you're distracted by the 4 pi, you can always factor it out. That's r cubed minus, well, that would be 8 over r squared. And all of a sudden, this is shaping up to be a rather easy problem. Again, a critical value officially would be r right there. But of course, it's not really a critical value because it's not even in the domain of the original right here once you've gotten it in terms of a single variable. And of course, it describes a nonsensical scenario, one in which your radius up here is 0. Okay? But you do have r cubed minus 8. R cubed minus 8, when you set it equal to 0, r is going to be equal to 2. Your critical value is r is equal to 2. And then from there, what we need to do is we need to actually answer the question. Now, did the question ask me what is the minimum surface area, or did it ask me for information about that scenario? Because you got to be very careful about what it asks you. It asked me to find the radius and the height such that the amount of metal needed is as small as possible. So it doesn't actually ask me to calculate. It asks me merely to find, okay? And of course, if r is equal to 2, I need to go ahead and plug that back into here. Here's where h and r are related. And if I plug a 2 into here, I'm going to get 16 over 4, or 4. So those are your measurements that describe the scenario that minimizes the amount of metal needed in that particular one. Okay? I'm going to go ahead and call it quits on this particular video. I'm going to look for a couple that are a little bit more hairy, a little bit more nasty for the third video on optimization. But since most teachers don't really hit this really hard, I'm not going to do any really nasty ones unless I'm asked. And go ahead and email me if you think that there are going to be ones that are pretty nasty on the test. Otherwise, we will sort of leave it at 3 videos, and I will move on to videos on anti-differentiation. As always, email me with any questions. Bye.